Okay. Oh, there we go. I can't quite see Marcus. That's all right.
Switch shoulder or anything?
Yeah.
Okay,
And we're recording. Okay. Welcome back to class. I see everybody's already picked up a piece of paper off my desk. You awake, David? You ready to do this? All right. So yesterday we were talking about wave energies and how we measure the energy of a wave by its wave length, the measurement between 2 points on a peak or the 2 points in a trough. Right? And so the further apart those wavelengths were, the lower the energy. The closer they are, the more frequent they happen, the higher the energy. So we have some words here on our word wall. We talked about those. Emit, a source of energy. Reflect, right? That's the quality of light that we were observing, those different colored things that we looked at. And we can quantify that from the formula that I showed you in measuring those wavelengths. And we also talked a little bit about the absorption of light. So for our entry task, I would like everybody to answer this question. On a cloudy day, does the sun shine less? Where does that light energy go? I want a complete sentence, please. You guys are middle schoolers, and I think you're capable of answering this. And look at our word wall here, our list of vocab words. You might want to select one of those for talking about where that energy goes. There's some good descriptors here, and we have some important information that might help you answer this. And while you're doing that, I'm going to get this screen to go, all right? The words are going to disappear, so you're going to think. We're going to be adding to our knowledge of waves, the electromagnetic spectrum. Everybody have a chance to write something down? Nice, complete sentences, everybody. Okay, so when we're observing waves, we talked about the light, right? We're going to add to our understanding of the way light travels. And we're going to use some signetics to talk about this and try to remember what we already know and apply that in new ways. Going to be incorporating some new concepts here. So this is a picture of Edmund Herschel. He was a 19th century guy who studied light by sending light through cut glass. And that caused the light to separate into different bands, as you can see. What he noticed is that he took some thermometers. And he noticed that the warmest end of the spectrum was beyond what he could see. It was beyond the red here. He has this thermometer set up. And that was kind of surprising because he didn't expect anything to be there. And his thermometers, and we can practice this. But from what we know about light, why is this? Everybody start thinking about this a little bit.
I'll give you a couple of minutes to jot down what you want to know.
Any responses? What do we know about waves already?
Some are larger or smaller than others.
Okay, and where is our red wavelength? From our assignments yesterday, I reviewed these, and looks like everybody put forth some more effort than others. Grant, you just wrote in the wavelengths there. Nice job, everybody. So where is red on that spectrum there? We've got a handout here in front of us. Tell me, what's apparent? What do we notice about this handout that you guys worked on yesterday? Red is big.
Longest wavelength frequency.
Okay, and that means what, Grant?
Very hot.
No idea?
Less energy.
Less energy, okay. I'm gonna get rid of this.
Anybody else want to?
Because we're going to be, like I say, adding to our understanding of how we observe. And what Herschel discovered is that there was something beyond what we could see. And as scientists, that's important, right? He made an observation. It was an incorrect observation. He's like, red energy is the warmest, most powerful wave energy, but that's not what we know now, is it? From our understanding. So we're going to add to
That might be just a lot of
our word wall with synectics. Okay, so think of name some things that light goes through, everybody.
Water.
Water, glass, air.
mystery.
Anything to add there?
Maybe the ones that come out at night.
That's called light transmission through translucent materials. Translucent or transparent, right? Everybody write this word down on the back of your entry task there. And we're going to come up with a picture of that, what it takes to get through glass, what it takes to get through a translucent or a transparent or transmission. Not like the transmission in your car, but kind of like a transmitter, like in emission, right? Transmitter. Just sending us signals, sending us wavelengths of light. Can you think of anything powerful enough to go through all these objects of glass and water? And that sounds like trans. David, you have any ideas? A train? Awesome. You guys can write whatever you want, but I like the idea of a train, so everybody draw a picture of a train. And then we're going to make a quick description of this. So I'll draw a picture of a train.
That's what mine looks like.
Right? Yeah. Many cars going on there. So translucent material is, can we see all of light when it goes through a translucent material? Translucent is maybe like those clouds, right? Not all the light's getting through. What's happening to that light? What did everybody write down?
Gets reflected.
It's partly reflected, so partial transmission, partial goes partially through. Transparent is all the way through, right? Going through. And transmission is a broadcast, right? Going through something. Broadcasting through. All right. So everybody get a definition down, a picture? All right, that concludes the lesson. We're going to continue to add to our charts here, our handout of different wavelengths, and kind of collectively work on this for our next lesson. Pause. I need to take a break.
All right.